Across a horizon of dunes, an elevated railway threads above a landscape that never stays put. The ground moves, the air scours, steel swells and shrinks with the sun. To survive here, every move has to be precise and repeatable, span after span. The mission is stark: deliver dependable, all-weather rail service across a shifting sand desert. Elevating the line keeps dunes from swallowing the track, but that only works if the geometry stays tight and predictable. Heat and wind push on steel and concrete. Bearings and rails must move as designed without losing alignment. Time is a constraint too. Temperatures limit safe work windows, so sequencing and rhythm on site are as important as strength on paper. The site is alive. Dunes migrate, flatten, and reform, sometimes across yesterday's axis. Wind doesn't just gust. It carries abrasive grains that can bury a road in hours and sandblast surfaces. Underfoot, heat and cold cycle through the day and across seasons, threatening to nudge bearings, rails, and fasteners out of tolerance if the AS-built line isn't precise. So surveyors establish control points and keep checking them. If the baseline shifts, pier centers miss by just enough to snowball into ride and maintenance problems. Misread the ground truth now, and you pour concrete in the wrong place. Think of the railway as 3 stacked layers that must cooperate. Foundations, a repetitive superstructure of piers and long pre-stressed box girders that let wind and sand move beneath. And the running system of sleepers, continuous welded rail, fasteners, bearings, and the sensors and communications that watch for drift so small, issues stay small. If the skeleton repeats, the trick is where you start and how you keep it straight. First, make access across the dunes. Bulldozers carve haul routes and level pads on the ridges so rigs can approach. Crews wet and work the top layer to knit grains where permit limits allow, using compactors and sprinklers so heavy equipment doesn't sink. A denser import layer may be spread and compacted to add bearing, and materials are staged just ahead of the advancing workface so the job can outrun drift. Those steps buy stable, predictable work windows and let cranes and drilling rigs target something that won't move. With pads firm, foundation teams drill through loose sand to reach competent ground, keeping bores open with casing and stabilizing slurry. Reinforcement cages are lowered, tied off, and surveyed. Concrete is placed from the bottom up through a tremie so fresh mix rises without trapping air. Pile heads are trimmed and connected into caps that spread loads and resist lateral movement. Quality depends on process and proof. Slurry levels and densities are monitored, fresh concrete is sampled, and finished piles are verified with industry testing methods and load checks so the design goal, penetrate competent layers and limit settlement, can be confirmed. Once piles prove out, crews repeat that truth thousands of times. Surveyors project pier centers from fixed control and mark them on cured pile caps. Small errors here become big later, so hold points and cross-checks are routine. Rebar and forms go up, concrete climbs to the designed bearing height, and teams keep a steady rhythm so curing, stripping, and reuse of forms cycle efficiently. Pre-stressed box girders are delivered and staged for lifts. Their geometry is precise, and careful handling avoids twists that would lock in stress. Track gangs follow with sleepers to fix gauge and position. Rails arrive in long lengths and are welded into continuous strings, then fastened to sleepers and ground smooth so the running surface is continuous across spans. At every step, alignment is checked in plan and elevation. If measurements drift outside tight tolerances, crews adjust before the error hardens into concrete or steel. The whole project advances like a convoy. Foundation teams, pier crews, launch or lift crews, and track gangs leapfrogging each other so the line marches forward without waiting on one bottleneck. All that repetition depends on one high-risk move: lifting and seating each girder onto its bearings with stop-and-check hold points. Planning begins on paper. Engineers pick lift points on the girder, size slings and cranes, and plot a swing path that avoids side loads. Wind limits and temperature windows are agreed before the first shackle tightens. The lift itself is slow and almost theatrical. Slings take the load and the girder rises with a faint creak. Taglines steady it. Spotters call small corrections. Precision instruments watch elevation and skew as the crane creeps in. At the bearings, everything pauses. The girder kisses the seats, and teams check contact, anchor positions, and geometry against the tolerance band. If any reading drifts, the command is simple: back off. The girder returns to temporary supports, shims or bearing positions are adjusted, and the crew tries again. Only when seat, line, and level all pass inspection do the cranes lower out and release. That pause and prove culture is how a delicate desert viaduct starts straight and stays serviceable. Two big choices drive how the work looks on the ground: where to make the big pieces and how to handle the rail. Precasting girders near the alignment shortens haul distances and keeps geometry control close to the workface. Using a distant factory can leverage established quality assurance but adds transport risk. Long welded rail reduces joints and maintenance but demands careful carrying and threading to avoid locked-in stresses. Automation helps pace the line when weather windows open. Sleeper-laying machines and tampers bring consistency, so crews can focus on the critical lifts. Quality control is a checklist you can replay. Visual inspections of concrete, bearings, and fasteners are routine. Non-destructive testing of rail welds and traceability back to batches keep problems small and fixable. When a weld fails inspection, the pathway is straightforward. Cut out, re-weld, re-grind, and retest until it passes. Load and response monitoring on selected spans confirms that behavior under trains matches predictions. When monitoring is deployed, deviations tend to stay very small, the sign that geometry and detailing are holding. Finally, the nervous system brings the structure to life. Power and communications connect stations, block sections, and control rooms. Temperature, wind, and intrusion sensors and cameras feed real-time data to operators so they can spot drift or disruption early. Designs favor redundancy and isolation, so a single failed device doesn't take down a long stretch. Commissioning is iterative. Devices are energized, thresholds tuned, and alarms calibrated until readings are trustworthy and nuisance trips are under control. Instrumented trains run across growing lengths of track to watch geometry, vibration, and thermal behavior under real loading, and data triggers inspections whenever readings stray from expected envelopes. Crews correct small issues before they grow. After an extended test period, the corridor opens to service, but commissioning doesn't stop. Teams refine maintenance windows, thresholds, and response playbooks as seasons change. The line now runs above moving sand, its shape held by planning, repetition, and that one precise operation. The slow, checked lift and seat that turned a hostile desert into a reliable railway.